Loud. So thank you, Dr. Bharadwaj, for accepting our invitation. So whenever you're ready, I would like to request you present your research. Thank you so much.
Yeah. Thanks, Rudra, for this invitation, and thanks everybody for being here. I'm gonna keep my talk pretty short so that you guys can ask me a lot of questions. So that's the main aim of this, and I'm gonna call my whole area of research as the deep microscopic quantum electrodynamics, where I'm really interested in understanding two distinct areas of physics when it really comes together, and then there is a marriage between them. One concept is this light, which you might know already from many of your high school and other knowledge. And the other branch is the matter. What I'm really interested is that what happens when the light is coming nearby to the material systems, and can we really use it to make new devices? That's the whole aim of my work. And probably I'll give you a very bird's eye view introduction of this. And the two ingredients in my research is one is the light. You might already know a lot of examples of light, right? A simplest example that we can think about is a light bulb. You can see all the light bulb in your classroom is really because of the light which is coming in, right? Another classic example is probably like a sunlight, which you will really see in the day-to-day life, that the light coming from the sun is what makes us see each other, makes it possible for the entire universe to function, correct? And a third example is even in the night light, where we see the example of the starlight coming into the earth, which is really the light which we will be able to see the light of the stars. And that's what makes us able to distinguish different parts of the star, correct? The other key ingredient that I'm interested in today's talk is the matter. So you might already know, again, from your knowledge, that matter can be classified into three main categories. One is the solids. That means that what happens in the solids. In the solids, when we take all of these atoms, and if we can actually combine those atoms and arrange them together in a very nice fashion, that's what makes us a solid, right? But there is also another type of a matter, which is the liquids, right? Like water, gas, or even like something like a kerosene or any one of these liquids. What happens is that the liquids doesn't have these very structured arrangements, but this liquid will flow through like a very like a water, very viscous flow, right? But even this liquid, when we heat up this liquid, what happens? That liquid will get converted into gas. That means that even in liquid, between these atoms, there will be some interaction, but when it's completely in the gaseous state, then the interactions will be broken off and all of those atoms will be randomly moving together independently, correct? So these are the two main ingredients of most of the physics that we do as well. And that has really puzzled generations of physicists that, okay, can I understand the light in one aspect? And can I also understand all of this different rich physics of the matter as well? And whenever we talk about any of these concepts in physics, the length scales is what really matters. And the length scales are what really defines the physics in which we are interested. So let's think about all the length scales different possible of the material system itself. So if I consider a man of a 6 foot inch, we can consider that man to be like made of 2 billion nanometer of the particles, right? And if we go into a much more smaller length scale, something like in the millimeters, like for example, even something like a blood drop will have like a 5 million of these red blood cells, and each of the red blood cells will be made of a diameter of this will be in the 2 to 5 microns. But if we go into a much more smaller scale, then that's where we approach both as nanometer and also picometer, right? So that means that whenever we talk about length scales, we classify most of the physics as the macroscopic physics when the length scales are somewhere in the greater than the 10 power minus 3 meters. And giving another example of the technological aspects is that if you really consider something like a semiconductor chips that you functions most of our computers, those will all function somewhere in this micrometer range. And the micrometer is about 10 power minus 6. But what happens if I go into a much more smaller length scale? That's where we are entering this regime of nanometer. For example, even in the biology, A 1 nanometer is about a these one strands of this DNA will be around 2 nanometer. So that means that even in a nanoparticles will have a particles of length scales of 5 to 20 nanometer. So the most of the physics which we talk about is always classified through this length scale. That means that if I'm really thinking about only the macroscopic or the microscopic, most of our classical physics will really work. But if I'm going into a much more smaller length scale, then we have to bring in the new rich physics of the quantum mechanics. So that's the length scales of matter. And whenever we think of the physics of matter, what I'm really interested in is that to explain how these atomic arrangements really exist in the material systems. And I'm also interested in how the stress, strain, and the phases of these materials. And we are also interested in, that whenever we have these matter or any materials like silicon, germanium, or any material system, there will be a number of electrons in that material system, right? Electrons are those fundamental particles, which is what makes the material system possible. And we are also interested in understanding how these electrons interact with these atomic particles. And most of the physics has been concentrated in this century has to understand and formulate like governing laws of this behavior of this matter. So that's the one side, that's the matter. But on the other side, there is also a length scales associated with the light itself, right? For example, if you are really thinking about radio waves, which is what we use to have a communication even in the radio frequency to go from one planet to the other or one building to the other, those were all in the 10 power 3 meters, right? But we know the electromagnetic spectrum, you may be aware of this, that the electromagnetic spectrum spans all the way from the radio wave, then it will also go into the microwave, which is in the 10 power negative 2, and also to the infrared and the visible, which is what the visible means, all the red, blue, and the other colors that we see. Those will have the wavelengths of around 10 power minus 6. So that means that the length scales of even the light itself also depends on the physics also depends on the length scales that I'm interested in. So that means that even when I'm interested in the physics of light, what I'm really talking about is that how the light behaves in terms of the behavior of the light in all of these length scales, and how do we really manipulate these, and how do we really detect these light itself in entire of these electromagnetic spectrum. So the physics of light really matters about formulating the laws governing this behavior of light. So this has really puzzled the generations of physicists, and the light matter interaction is really central to all of the physics that we talks about. So that's why whenever I start any of my talk, I start by saying is that the life is really interesting because of the light matter interaction, right? Think about this. We see this, beautiful pictures of the solar system, and why that is really possible is really because of when you have a starlight, even when inside of any of the stars, there will be a number of different materials, right? And when these materials are heated, or when these materials will interact with each other, those will emit some light. So those light is what we see from Earth, right? So that means that this rich physics of astrophysics can all be understood mainly because of the interactions between the light and the material system. And also, even in the biology, another very prominent example is which you might have studied even in your high school, is this photosynthesis. The phenomena, the way it happens is that the light is coming in and hitting in these leaves, and these leaves will undergo some microscopic mechanism, and that is what makes these plants to grow or the fruits to come out and everything, right? So to understand all of this in a physics level, what we really need to understand is that how this light interacts with these materials. And we know as physicists, we always carry the mathematics burden all the time with us, right? And we are not satisfied when we talk about only that, a very hand-waving way that, okay, this is how it happens, but we want to put some numbers into each one of them, right? So we want to quantify in a correct term, we want to quantify this interaction. That means that every material, we want to quantify that how much strength does it has for this interaction with the light. And these are the two main questions that were driving the entire physics, that how do we quantify this interaction? And what are really the implications of these kind of interactions? And this has really puzzled the generations of physicists, including some of my research as well. that if you think about the whole history of physics, where the main ingredient to understand this light matter interaction is that I'm going to come to this slide in a minute, that this brief history I always like to talk about, you might not be aware of all of this laws, but one of the exciting thing of doing physics is that as you grow from your bachelor's to even graduate studies and later on, that always you are migrating in understanding all of these laws. So you might be aware of even this Newton's Principia. This is one of the most foundational aspect of physics. I'm sure Rudra talked about a lot even in this course as well, that the Newton's laws in a fundamental level is describing the behavior of matter. In a century forward, even the invention of the chemistry, where we were able to classify different elements of the chemistry, is again understanding of this matter, which has led into even something called the Avogadro's laws. In a parallelly, when you think about the history of physics as well, there was already several of these experiments. You may have heard of some of these experiments, but you might study later on in your undergrad studies as well, that people were trying to understand the behavior of the light itself. So there were two branches, one is the matter and one is the light, but only from the advent of this quantum mechanics, we started thinking about this both light and matter as the two sides of the same coin, and we started treating them together in interaction in a fundamental way. And one way you can already see it is that if I'm really going from the left to right here, what I'm really doing is that I'm reducing the length scale further and further. For example, if I'm thinking about this Newton's Principia, I'm thinking about the physics in the macroscopic level, but as I go through this scale, I'm really reducing the scale. And my work has been concentrated on understanding this light matter interaction, as I talked about, even going beyond the sub-nanoscale level. And why that really matters, and this is really fundamental questions that I'm trying to understand, is that when the light is subjected to a material system, the electrons in the materials will start vibrating, right? So we want to understand how these electrons will vibrate with each other. And depending on the strength of these electrons attached to the nucleus, there is a light frequency which will interact with the natural frequency of the material. We want to understand that. And there is also another phenomena which happens is that when the light hits in these electrons can also get excited. You can think of it like you are stepping a stone, that let's say that you have a kind of a marble over here and you hit the marble with another marble, that marble can get bounced off into a next step, right? So that's what the excitation. So we are interested in understanding these excitations as well. And these electrons are also particles, right? So that means that these electrons can hit each other. We're interested in understanding these collisions as well. For really to understand all of this, that's where the quantum mechanical ingredient comes in to provide the formulations and the framework to understand this. And another, to give a very bird's eye view that why the sub-nanoscale light matter interactions are important. And again, you might have heard of these terms quite often in your popular science articles and everywhere as well, that we are really entering an era of quantum 2.0, right? Where that means that from the semiconductor chip, which was all in the microscopic levels, that's what built our modern computers are, we are moving into a quantum devices which are really in the sub-nanoscale level, right? So that means that there are many areas evolving in this. One is the quantum sensing, where we are really trying to utilize these ingredients of quantum mechanics or these quantum devices to sense the properties of some of these materials. For example, this is something like, let's say there are these cells in the human atoms, and I want to image these cells. So then these quantum sensors can help us. And there is another evolving field of this quantum communication. That means that think of it like I have a probe station which is in the Earth, and I have a probe station somewhere in the Mars, and there is also a satellite somewhere sitting in the other universe. If I have to really communicate with each other, I have to build in again, that's a light matter interaction, because the communication channels are all light, but the detection channels are all the material system. Another big area, which you have again heard of, is this quantum computing, where we are really trying to understand, use the dynamics of this quantum mechanics to achieve a computation beyond our traditional 0 and 1 computation of what we do in the classical computers. So to understand all of this in some way, that it boils down to understanding the light-matter interaction. And my research has been building the tools for this from a theoretical way. One is that if you want to realize these devices, we need a material system. We need to have the understanding of these material systems and how this will interact with light. And that's the fundamental understanding. Once we have the material system, we will build in these devices. So that's the quantum device modeling. And since these systems are so complex enough that our pen and paper calculations will never work, you need to code in these calculations in a computer system to achieve these calculations in a much more faster manner. That's where we will bring in the knowledge of the computational electromagnetism. So combining all of this, what we call it as the predictive analysis, that means that instead of doing the experiment, we will build in these rich knowledge to provide the parameters that we can actually measure experimentally. That means that if I build in any of these quantum devices, I will tell the specs beforehand to the experimentalist through the development of what we call it as a scientific software. So that means that we use our physics knowledge to build these software systems so that we will influence the experiment and the development of these devices, which will lead into not only the discovery of the new phenomena in these light-matter interactions in the sub-nanoscale level, and also several of these new devices to influence the development of quantum technology. So that's where I'm calling this whole framework as the computational quantum design, because we are really influencing the device and the generation of the next generational quantum technology based on our physics knowledge. And that's what makes this field very exciting. I'm just going to pause here for a minute before I move on to see if there are any questions, or I can spend the rest of the time for the questions as
well. Yeah, do you have any questions? Yeah, Ashik has a question.
I'm still a little confused. What is the vibrating electron?
What is the difference between vibrated electrode and excited electrode?
Sure. Yeah, that's a very nice question. So think of it like this. Let's see if I can draw somewhere over here. But anyway, it doesn't matter. I'm going to show it over here. Maybe you can see it. So think of it this one as the electron, and the light comes in. And when light comes in, this electron can vibrate like this, right? So that's the vibration. So think of electron like a marble. Then if you have a marble, then you hit in with another smaller marble, then this marble can move, right? Then this move, if there is another somewhere wall or something like that, this marble can hit that wall and come back, and it can vibrate like this, right? So that's a vibration. But there is also something else can happen. Let's say that this marble is sitting on a steps, okay? And you have a marble in the lower step, and you hit that with a smaller marble in a very high force from the top. Then this marble can jump off and go to the next step as well, right? So that's the excitation. So that's what we talk about in the two differences even in a fundamental level in a material system. That is what happens as well. The vibration really happens because these electrons are also charged, right? Because these are not really neutral particles, they are charged. And there are also nearby electrons, which will also, whenever there are positive and positive electrons, those two will repel each other. So that means that will cause the vibration. But there are also steps in the system itself. Because of this, when you hit in with another smaller marble, that's like your light, this electron can go into a top of the step. That's the excitation.
Thank you. Other questions? No question?
Because of the energy required, or like how energy is quantized between steps you were talking about? Is that what you mean? With the jumping?
So what Akib is asking is, it is because of the quantization of energy?
Yes. So in atoms, what happens is that there are these energy levels. That's like your steps, and initially your electron will be in the ground level. That means that your electron will be in the lowest of that level. That's the quantization. But whenever light comes in, that will carry some energy, right? So that energy will be absorbed by this electron, and then it can move into a next level as well.
And if we don't have enough energy, it vibrates. Is that what?
Yeah, if the light is coming in with the lower energy, there are also different degrees of freedom. This electron can go on top of it as well, but this electron can move and vibrate as well. If it is low enough energy that, if the steps is like this energy scale is like larger. But if there are smaller energies, then the electrons can just vibrate instead of jumping into the next step.
They jump once, then they also drop. What makes them drop, and why do they lose that energy?
Sure, yeah, because that's another exciting quantum mechanical concept, that the universe, right? Universe is somewhat lazy because we always want to, in a sleeping state. So that's what even the electrons prefer as well, that they always, in a physics term, want to be in a equilibrium state. That means that we always want to be in a as lower energy state as feasible. So that means that even when the universe is excited, even the electron is excited, the quantum mechanically, it is always favorable to come into the ground state, come into a lower energy or the more equilibrium state. So that's what makes most of our physics very exciting.
Thank you. Sophia has a question.
So, like, in terms of like light interacting with are they really only interacting with and like affect like electrons on like
Oh, yeah. The question is, when light does the interaction with atoms, does it interact with only valence electrons or all other electrons?
Yeah, that really depends on the energy of the light coming in. So you can think of the whole solid state system like a soldiers. Okay, your valence electrons are the foot soldiers, which are sitting in the outermost level. But then there are also other different type of soldiers who are sitting inside the more and more castle as well, right? Your light is something which is coming in, penetrating through those soldiers. So if your light comes with a low enough energy, then it can penetrate only the outermost soldiers. That's your valence electron. But if you keep increasing the arrows, or if you make these arrows sharper, that means that your light is becoming stronger. You can go into a much more deeper level electrons as well. So that's why this physics will have a different degrees of freedom. That means that you always treat the physics first by the length scale that I'm talking about, then with the energy scale I'm talking about, then also with the momentum scale that I'm talking about. So depending on these, each physics can be different.
Thank you. Other questions? Yeah. So you have more presentation, right?
I was just going to give one example just for fun on the
Okay.
some.
Yeah, thank you.
Yeah, I still have like a few minutes, or
Yeah. So, yeah, please continue the presentation, and then if there are more questions toward the end, probably we'll do that. Thank you.
yeah, sure. I'm just going to show one example of how these kind of your computation and your theory can really influence the real world devices. Because sometimes, quite often, when we are dealing with physics, we talk about all the fancy stuff, and always we lose the touch of the real world as well, right? How we are really can influence the technologies as well. So this is just a cool cartoon right now, doesn't matter where it is. So this is one very nice material, which is like a tellurium. And forget about how this material tellurium is. This tellurium will have a very nice atomic arrangement in such a way that, think of it like a screw, and the screw will have hinges going around like this, right? So the tellurium will have all the atoms arranged on the hinges of those screws. So this is the light going through this tellurium, that when the light go through these kind of hinges of these atoms, they will start rotating. So we thought about, we were able to understand this physics in a very rich way through many of our work. Then we were like, okay, can we use this for any applications, or any real world disruptive applications? And we know that the imaging solutions, or the cameras, or let me just call it as the cameras, are quite important, right? You have your cell phone cameras, you have your cameras that you take all the pictures. How does those cameras work? These cameras work in three main technologies, but I'm going to explain only one of them, which is like the simplest. That what this camera is doing is capturing different wavelengths of the light existing in your image, right? That means that if I take an image, there will be different colors of blue, different shades of green, blue, red, everything. And this camera is going to separate out all of them, then merge all of them together to give you the very nice picture, right? So what we were able to see is that in a tellurium crystal, that if you are, imagine this is like a blue light and a red light coming in, that since the light really rotates inside these crystals because of the very rich interactions happening over here, that when it comes out through that tellurium crystal, your red light and your green light will get rotated at two different angles. So that means that your red light and your blue light are two different wavelengths, right? Because those wavelengths of these two colors are really what defines them as two different colors. So that means that using this rotation framework of the two red light and blue light, we can separate out two different colors. So this is not very important when we did some theory work for this but we did the experiments for this as well. That think of it like a goggle that you have, that you wear when you are going out in a summer day like this, that typically when you image that goggle, they will only have these kind of intensity map, right? But through our camera, which we designed through these type of a tellurium crystal, what we were able to show that even this kind of a goggle will have a very rich, because of the tension existing in the glass of this goggle, that there are different shades of red, different shades of green, and everything, etc. So that means that in a typical camera that you are taking an image where you're really taking a red, green, and the blue images of this, that means that you are really taking these images of this car like this, that this car is blue, this car is white. But through our camera, this kind of a tellurium-based camera, we can capture not only these type of RGB images, we can also capture these type of hidden data existing in the glasses of these car and the other leaves of this car and everywhere, leaves of this tree and everywhere. So we are really entering this era of machine learning, right? You might have heard about this. In this data science and machine learning, let's say you are driving a car at night, right? You want to drive a self-driving car at night. That means that this car needs to capture the images surrounding it. This car can function in a broad daylight which can capture the RGB images. But these kind of a rich data existing on these glasses and everywhere else persist even at night. So that means that by capturing these type of a hidden information through our material science knowledge, we can influence even something like a driverless car, even the machine learning algorithm, etc. Because we're able to gather more of this data, and that can provide us better understanding of this imaging framework. So that means that almost going from the fundamental our quantum mechanical and the all the fancy theoretical knowledge, we can reach even the very technological advancement. So that's where the physics is always very fun, that you are sitting in a area that you can always make a big influence to the newer developing technology through your physics knowledge.
Thank you so much, Dr. Bharadwaj, for the presentation. Do we have any other questions? Asit has another question. Yeah, please.
So these tellurium cameras, do they use visible light or do they use other?
These cameras use visible light or other wavelengths?
These cameras can function from all the way from the visible wavelengths to even to infrared wavelengths. So that means that infrared wavelengths are which we won't be able to see, right? That's the only heat radiation, right? But even at night, infrared radiation exists, right? So using that infrared radiation, you can actually capture the images even at night. So that's the beauty of these type of cameras.
Thank you. Other questions? Okay, it looks like that everybody is happy. So thank you so much, Dr. Bharadwaj, for this outstanding presentation.
Yeah, one last thing I wanted to mention. I had this, I'm running this, these seminar series might be a little upper level for some of you, but at least the introduction, there are very rich material science and optics. Introduction of some of these seminar might be interesting to many people. If you are interested, feel free to visit this YouTube channel. There are many talks from several experts which might be of interest as you're growing through this physics journey.
Okay, thank you. Thank you so much. If you would like to take the QR code, please take a picture.
Sure.
So thank you so much, Dr. Bharadwaj, for this presentation. So we wish you have a nice day. So probably we'll
Okay,
see in a few days. Right.
Yeah, thank you so much. Have a good one.
Thank you.